to my Crackpot Theory. This is my theory of everything, okay? Where I try to explain all fundamental forces in one underlying framework. Before we begin, I want to show you the theory of everything, okay? It's very simple. Check this out. This is it. This is the theory of everything. Now, it can be expanded a little bit more, like this, but generally, this is the behavior of what is fundamentally going on at all scales. Now, a good scientist has very few assumptions when they are coming up with a theory. In my case, I have a shit ton of assumptions, and I'm just going to give you 10. This will just give you a rough idea of the direction we are going to be heading towards in this video. I'm about to say something wild. When I was working at the factory, I was thinking about quantum entanglement. Now, for 12 hours a day, I was standing in front of these coils of wall base. What I realized was these coils of wall base were analogous to quantum entanglement. Both coils are rotating in opposite directions, and that's just to represent the angular momentum or spin of two hypothetical electrons that have entangled. I imagine that both of these coils were physical particles that had locally interacted in some way and had become entangled. Because I did this, I then had a metaphorically physical quantum phenomenon right in front of me, with which I could interact with and experiment. If we're measuring position and we have two entangled particles in a box, and we find one particle in the top left corner, we know with high probability that the other particle is in the bottom right corner. Now, if these coils are hypothetically entangled particles and we are measuring position, you can imagine that the factory is this box. If I interact with one of these coils by placing a finger on it, I will find the position of the particle that I interacted with. The little purple squiggly lines are to represent the probabilistic nature of finding that particle. So it is a certain probability that if I place my finger somewhere in this factory, I'm going to land on a particle. And that should tell me with high probability where the other particle will be within this factory. Based on the Heisenberg uncertainty principle, now that we know the position of these particles, we now know less about the angular momentum of these particles. And this works both ways. If we know more about the momentum, we now know less about the position. Now let's measure the angular momentum of these coils. Because we're measuring the momentum, that means we won't know the position of these particles. So if you imagine yourself blind, okay, you're blind in this factory, you're looking for these particles, they're entangled and they have angular momentum and they're rotating, and you brush against one of these particles. And this will instantly tell you, based on the angular momentum of the particle that you interacted with, which particle is spin up and which is spin down. For this analogy, I think it's important to know that both coils share the same speed. Okay, it is only the bottom coil that is actually rotating. The top coil is static, it's not moving. But if we hypothetically entangle the tissue paper into the bottom coil, whatever speed the bottom coil is, the top coil will share that speed because it is the bottom coil that is pulling the top coil in. This is analogous to the conservation of angular momentum. Now, as you can see, when I interact with the top coil, the paper rips. I interpret that as the wave function collapse. Because of this, upon measurement, I instantly know the spin of both particles. We know that if we're measuring entangled particles, it doesn't matter which particle we choose to interact with. The wave function will collapse upon measurement of either particle. So what this means is that it doesn't matter if we measure the top coil or the bottom coil, the paper should rip. When I interact with the bottom coil, the paper instead warps. Obviously, entanglement is a quantum phenomenon, so I shouldn't have the same exact interaction with a classical object that is analogous to entanglement as a real entangled pair. That being said, the warping of this paper intrigued me because there have been theories that have pondered if gravity is actually emergent from the entanglements of these particles. Throughout this video, and based on this particular setup of these coils, I interpret that as gravity. Yep, there's gravity. I sincerely want you to know that as I'm pulling this information out of my ass to try to explain to you my theory of quantum gravity, I'm probably wasting your time. So yeah, I'm just throwing that out there. So what is causing this warping? Well, mass. We know that mass warps space-time. and the curvature of space-time tells mass how to move. What mass is causing this curvature? I have no idea, but obviously it is separate from the two entangled particles. Because I don't know what this mass is, I used supersymmetrical particles as a placeholder for this mystery mass. Then I was wondering, well, if the standard particles can become entangled, can supersymmetrical particles also become entangled? And when do they become entangled? A lot of the pictures that I share with you is my thought process and how I got to my conclusion for a lot of these assumptions that I will make throughout this video. So the first possibility is that the Susy particles are always entangled, respective of the standard particle fate. Another possibility is that both are entangled at the same time. What I landed with was that there is a superposition of entanglement between the two types of matter, so that when one is entangled, the other is not. Essentially, both types of matter can be entangled at the same time, but upon measurement, you notice that it is only one type of matter that is entangled at one time in one quantum entanglement system. Basically, what I'm trying to say is that entanglement is not the interaction between two particles of one type of matter. It is the interaction between four particles between two types of matter. So again, if the standard particles are not entangled, then that means the Susy particles are entangled, and vice versa. If the standard particles are entangled, then the Susy particles are not. So what information can we get out of this? Well, what I inferred is that the distance of these entangled particles matters. For example, when the distance of entangled standard model particles increases, the locality of supersymmetrical particles also increases, and vice versa. When the distance of entangled supersymmetrical particles increases, the locality of standard model particles also increases. Now I want to talk about decoherence. This is a major part of understanding why we see the world in our classical way. Okay, let's just hypothetically imagine here, what if decoherence is actually linked to the entanglement of superpartners? Basically, there is an exchange of entanglement between the two types of matter, and entanglement never actually breaks. It helped me to distinguish two types of decoherence. It's kind of a general term for the loss of coherence of a quantum state. This just kind of gave me a better way to think about it when I was distinguishing between the exchange of entanglement and persistent entanglement. And we'll get into that later. Within strong decoherence, this is where we get the exchange of entanglement between the two types of matter. This is also where we have local interactions between like particles of the two types of matter. And this is also, if you think about the measurement problem, this is also where we get definitive states upon measurement of a particle in superposition. Weak decoherence is when the entanglements are less likely to decohere, so that's why I say persistent. Now, because weak decoherence is not definitive, I think this is where we find the probabilities of our universe. So if space and time both emerge from these entanglements, then could we also say that time itself has decoherence? So the strong decoherence of time would be the present moment, or now. And the weak decoherence of time would be anything that is not now. So that would include the past and the future. Here I just kind of went into a deeper dive on this idea, but at this moment I really don't want to talk about all this, so I'm just going to plop it here for you and you can check it out later, or now, and just pause the video, and we're just going to move on. Now, what happens if we entangle two particles? Well, based on this idea, that would mean that the previous entanglement of Susy particles in that specific location is going to break. Why? Because our particles are about to become entangled. This also means that when we make a measurement on one particle of an entangled pair, that is going to create the entanglement for Susy particles in that location. In one entanglement system, the particles will travel to and from the point of locality, what I describe as the time and place of when entanglement is either, quotation marks, broken or created, quotation marks. Now, it is only two particles that are interacting with the point of locality at one time. So, could we possibly say that they have opposite temporal localities? Why? Because it takes time for either the free moving particles to become entangled or for the already entangled particles to decohere. It takes time. Now this exchange of entanglement, or this creation and breaking process, happens at the same time. The way that I thought about this, it seemed like it was instantaneous, but we know that nothing can travel faster than the speed of light, so nothing is truly instantaneous. So could we say that this exchange happens at the speed of light? Question mark? I don't. This exchange of entanglement is not going to happen magically, okay? I believe we're going to need something to mediate this flipping. One idea that's been circulating for a while, ER equals EPR. That basically means wormholes. So wormholes is what mediates this exchange of entanglement. I want to just put this wormhole idea to the side because we've just been talking about one system of entanglement. What about a large group of entanglements in a large region of spacetime? So now if we're looking at a large region of spacetime where, for example, let's just say the standard model is not entangled. Based on this idea, that would mean that locally in this region, the mirror model is entangled, and vice versa. If the mirror model is not entangled, it would mean locally in that region of spacetime, the standard model particles are entangled. Alright, now because distance matters, when the locality of standard model particles increases, that'll mean that the distance of entangled supersymmetrical particles also increases. So this spaces out the entanglements, and vice versa. When the locality of supersymmetrical particles increases, this will space out the standard model entanglements in that region of spacetime. Since this is a larger region of spacetime, this is basically equivalent to anything that is part of our classical world. If we go back to the idea that gravity emerges from these entanglements, what can we infer about what we have already learned? Since there is a superposition of entanglement between the two types of matter, there can really only be two possible futures for one entanglement system. Either the system persists or the exchange occurs. I am proposing that when particles gain mass, this stops this exchange and the entanglement persists. Now we can keep on adding more mass and eventually get something that looks like a planet. As you can see, the planet has all of its standard matter in one local spatial region, but also the non-local entanglements of all of the previous matter. This non-local local shit is really fucking confusing, but the Susy entanglements had to interact with their own point of locality at some point, and so it is also non-local temporally as well, because they entangled at a different time, way in the past. Another thing that I inferred is that these particles don't really like to be near each other, either if the entanglement is exchanged or if it persists. Even though these particles don't want to be physically near each other, temporally, within time, they are interacting. They do eventually interact with the point of locality. So it is, could we say that opposite temporal localities are attracting each other the same way that a north and a south magnetic field attract each other? I don't think there is any correlation, but this is kind of just how I was trying to understand it. The fuck if I know. Even though these two types of matter don't typically like to be near each other, one place in the universe where they are, where the free moving particles are all gravitationally attracting each other, because all mass attracts, is within a galaxy. Through time, on a massive scale, that is how I think galaxies could form? Question mark? So if mass warps spacetime, then could we assume that anything of the standard model that warps spacetime is warping the Susy entanglements beneath it? Now I just want to take a step back and show you what happens when we start scaling things. Something really cool pops out. We can start with small masses, such as you or me, scale it up to a planet or to a star, and one thing that we all share in common is that we're made up of standard matter. Could this also apply to black holes? Well, I think so. Initially, they are made from standard matter. If we scale up to a solar system, the same concepts still apply. But what happens if we scale up to a galaxy? That is when shit gets really cool. So if we think about our mass, well, our mass is made mostly of standard matter, but in a galaxy, most of its mass is made up of dark matter. Did you know that supersymmetrical particles are a great candidate for dark matter? Well, for this video, I'm gonna say yeah. So now, if we have the locality of dark matter increasing, that also means what? The distance of entangled standard matter will also increase. So what happens if we keep on scaling? Since galaxies are made mostly of dark matter, and most of our universe is made mostly of dark matter, if we keep scaling to galaxy clusters, to the cosmic web, and ultimately the entire universe, we see that dark matter is counteracting the force of dark energy, which is entangled standard matter? The fuck? Anyways, if this is a black hole, then what's the opposite of a black hole? Well, a white hole. This is another depiction of the same process, but instead it just shows you the path that this matter is following along, which is its world line, which could be the entanglements of these counter particles. This is just another example of what the space-time fabric could look like with these superpositions of entanglements interwoven together to create the space-time fabric that we are familiar with. Alright, so let's check this out. This is a curved black hole, which is basically a rotating black hole, and it's thought that most black holes rotate. Within the math, out pops a ring-shaped singularity, and it got me a little hungry. It reminded me of a donut. So basically, a black hole is a pink donut, and a white hole is a purple donut. And if you smash those two together into one pink purple donut, then you got yourself a curved singularity, a ring-shaped, all that hoo-ha. Now I want to talk about the before and after of a black hole. Before we can have a black hole, we need a white hole. When the standard entanglement breaks and the mirror particles become entangled, this allows for the formation of matter, such as a star, and eventually a black hole. This will reopen up the exchange of entanglement, baby. And if we go over the white hole, well, before we have a white hole, we need a black hole. And when the Susy entanglement breaks and the standard particles become entangled, and remember this happens at the same time, well, remember distance matters, so when the locality of the supersymmetrical particles increase, that'll space out the standard entanglements, and big boom. Alright, so based on these ideas, let's just speculate what could happen within the singularity. As the black hole consumes matter, it grows. So that in turn grows spacetime. Eventually, the wormhole will open, cutting all of the Susy spacetime entanglements, so this infinite curvature. This will eventually form a singularity of Susy matter. With no more matter to eat, the black hole will begin to shrink faster and faster due to Hawking radiation. When the black hole has eventually evaporated, that is when I'm thinking the wormhole will open. When the wormhole opens, it's going to do two things. It's going to cut all of the previous Susy entanglements, so then you know there is no more black hole. It is completely evaporated. But it will also entangle all of the standard matter that fell in. This means that all of the standard matter that fell into the black hole will become the new spacetime for the new universe. The wormhole will close just as quickly as it opened. When the wormhole closes, that is when I think the white hole opens up. And now, because there is so much Susy matter in one spot, it's going to force all of the entangled standard matter to expand drastically. Now, you may be asking, well, if we have all of this Susy matter in this new universe and all of this entangled standard matter, well, where is all of our matter, the 5% that we are familiar with? How did we get that? Well, I think, what if all of the entangled particles that fell into the black hole, since they are already entangled, they will not be entangled when they pass through. So all of the particles at the other end of Hawking radiation could be the new normal matter that passes through. Based on this idea, I think your fate falling into a black hole could actually be worse than spaghettification because, well, you're not even going to become new matter, you're just going to become the new spacetime, and that sucks. So if you want to escape on the other end, you might need to already be entangled some way. Imagine if you had an hourglass, but the sand that falls to the bottom will become the bottom half of the hourglass. We will only see one side of the hourglass at one time. And the glass up top will become the sand for this new cycle, and it could just repeat indefinitely. If we can have standard particle Hawking radiation, can we also have Susy particle Hawking radiation? We know that when a black hole begins to shrink, it is emitting this standard particle radiation. But what about if it's growing? Will it emit Susy particle Hawking radiation? So it looks like while the black hole is shrinking, it's also consuming free moving dark matter particles. And since those particles are not entangled, those particles will be the entangled particles in the new universe. It's basically the Susy space-time fabric that we are sitting on. Now let's go into the new universe and see how time moves forward for both particles. These free moving particles are still acting as if distance matters and that locality matters. And it's like they're not physically entangled, but it could be like a phantom time entanglement. So this is time moving forward, and this is time moving backward. Time moving forward for all black holes means they're all going to shrink. They're all going to evaporate at some point, very far into the distant future. But time moving backward, that means, well, the black hole is going to shrink. Because, no, actually, fuck that. It's going to grow. So how do we test this? So basically, you just want to get a crap ton of entangled standard particles, and the greater the distance, plus the longer they are entangled, will give us a greater gravitational effect. And because the Susy particles are entangled in time, eventually they will show up at the point of locality. Now they could be at the other end of the universe, and if they have mass, that could take quite a while. But maybe they were traveling the entire time, and so they will just show up. Another way that we could possibly test this is using an experiment that will entangle two photons together at birth, spontaneous parametric down conversion. And basically, if the superpartners are real and in time they do interact with the point of locality, which would be the crystal, when the entanglement of the photons will break, that is when the photinos will collide and entangle, and for that fraction of a second, that crystal will gain the mass of the photinos. So basically, we don't even need a new, bigger, billion-dollar super collider to find these superparticles. Maybe for other particles at higher energies, sure, but for superpartners, and based on these ideas that I brought up, we don't need any of that. We got experiments that we can already test. Okay, so the next part of this video is pretty abstract, and I don't really care to explain it, and I don't even remember half of my logic for it. So we're just going to fly through this. I don't think there's any meaning behind any of this, but I drew some pretty pictures. I was just like, oh, well, what kind of cool patterns could emerge by connecting these dots of entanglements between space and time? And yeah, I just connected the dots. It was pretty fun. So we just saw some space, and now here's some time. Basically, the space is horizontal, time is diagonal, and yeah, then we got some space-time. That's cool. Penrose diagrams kind of pop out. That's pretty neat. I think that's just kind of a coincidence though. And then we got some cool space patterns. Check that out. I like the flower one. That's neat. I just rotated the matrix a little bit. And here's some time. That's neat. And then here's some space-time. That's pretty cool. Oh, and here's time becoming longer with more mass. That's kind of my explanation. I don't want to explain it. Obviously, if you hadn't noticed by now, I am not a scientist, okay? I'm pulling this information out of my ass. Well, my idea, basically, out of my ass. And I really don't know what I'm talking about. That the information that I got, I mean, it's all other people's work, essentially, and I just put it all together. I still feel like I should cover my ass, in a way. Even though I have no ass to cover. Don't take what I say literally. It's just for fun, because I'm a crackpot, and I mean, just y'all need to be aware of that.
You explained to me, and I've said it here, the fabric of space-time might be woven by wormholes that connect the virtual particle pairs that come in and out of existence.
So it's like a little quantum net holding the whole universe together.
Exactly right. We find mathematically, if we cut the threads of quantum entanglement, space falls apart. It discretizes into little tiny pieces and then just disappears.
I gotta go.
Okay, so I've explained gravity as best as I can through my crackpot logic. If you still want to stick around, I'm going to try to explain the other three forces. Okay, so let's begin. For gravity, the cause are these entanglements, and the effect is mass, or persistent entanglement. Now, mass is an attractive force, but what happened before that was a repulsive thing that dispersed all of these Susy entanglements. Okay, so since these non-local entanglements cause the local mass, I want to utilize this for the other three forces. So the cause is non-local and the effect is local. Okay, so since gravity is an attractive thing and what happened before that was a repulsive thing, basically I'm implying that there is a opposite interaction happening in the past to create the local interaction in the future. If we apply this to the electromagnetic force, the non-local cause creates the local effect. But again, the interactions are opposite from each other. Instead of a repulsion, there is an attraction. So we could say that, for example, all of the non-local entanglements are negatively charged and the particles they are interacting with are positively charged. This implies that they're exchanging photinos, possibly. So all of these non-local interactions happen in the past, and in the future you get a local interaction, which is the opposite of what the non-local particles experienced. The weak force, a local emission of a W boson, would imply in the past all of the non-local Susy particles are absorbing W bosons, and vice versa. If the local interaction is absorbing, then the non-local interaction in the past was emitting. Now, I think this could hypothetically work if everything was conserved and it played out just perfectly. But I just think it's super highly unlikely that all of these non-local entanglement particles are colliding simultaneously and having the exact energy and momentum required for the reaction locally in the future to occur. So, yeah, this is difficult to wrap my head around for sure. If all matter has these non-local partner entanglements, then so would the fundamental particles, right? So each would have a finite amount of entanglements varying in distance. For example, protons and neutrons would have non-local Susy entanglements. Now if we look inside a proton, well, it can get a little complicated, but basically there are these quarks, and they are the most fundamental particles as of our current understanding of particle physics. What binds these quarks together are gluons. This is the strong force. I'll get back to the strong force in just a second. But since quarks are the most fundamental particles, they would have the most basic entanglements. So they would have the fewest number of entanglements. So hypothetically, let's just say, as of now, each quark has just one pair of entanglements. So maybe outside of the proton, the outer vacuum shell is just as active as inside the proton. Okay, so then could we infer that non-local quarks relative to the proton is equal to the local quarks within inside the proton? So basically, what is conserved on the inside is also conserved on the outside. Now going back to the strong force, it gets stronger as quarks get closer together. This is a unique property known as asymptotic freedom. As quarks move farther apart, the strong force between them increases, making it increasingly difficult to separate them. This is why we never observe individual quarks. They are always confined within hadrons like protons and neutrons. I just read off some ChatGPT. So basically, that would imply that these quarks are repelling each other instead of attracting. So the farther apart these quarks are, the closer together these quarks are, and vice versa. The farther apart these quarks are, the closer together these quarks are. Here are some more ideas that I have. Maybe the entanglements fluctuate in distance, like orbitals in an atom, where certain distances cause local phenomena to be altered in a certain way. When I was learning about the Mobius strip, I realized that you could do the Dirac belt trick with my coil analogy, or you could do my at-home toilet paper example. That works too. Alright, so what if Dirac's belt is literally these entanglement planes, or the boundary for these particles, or bulk? So when the exchange is supposed to occur before they separate, what if the world line or the boundary for these particles twist like a Mobius strip before separating, and so that when they have separated, all particles traveling on this boundary will be predetermined based on the pre-twisted world line? Would this explain superposition? So based on whichever pre-twisted world line these particles are traveling along will determine which spin value these particles have. For example, all the particles on the top world line will be spin up, and all the particles on the bottom world line will be spin down. Maybe the height of the band is equal to the size of the particle. The width would just be a one-dimensional line. Trying to learn a little bit about the Hopf vibration. It's really complicated. I don't know how to think in the fourth dimension. I wrote down a few little notes. I don't think there's any correlation. Let's just move on. Hypothetically, as long as the parent entanglement has not decohered, could new entanglements be created within? So all of these free-moving particles would be interacting with each other within their own bounds. So the Susy matter interacts with itself within standard entanglement bounds, and standard matter interacts with itself within Susy entanglement bounds. So Susy atoms and everything within its boundary can not only interact with themselves, but also the non-local entanglements for standard atoms. So the free-moving Susy particles can interact with these entanglements, and also atoms can interact with these entanglements, and also the non-local entanglements for bigger objects like stars and planets, and vice versa. Just another example, I believe that this would only work if everything was conserved. So energy and momentum and all of those particle properties are conserved. If that is all good, then I think it checks out. Otherwise, it's wrong. ADS-CFT correspondence is a key example of the holographic principle in action. Here's another thing I'm going to talk about that I really probably shouldn't be talking about, but fuck it. Basically, this is just a flat two-dimensional hyperbolic universe where all parallel lines diverge away from each other. So a Susy bulk in this example would be created from a system of maximally entangled standard particles, and vice versa. Standard bulks would be created from maximally entangled Susy particles. Yeah. The boundary of this two-dimensional flat universe would just be a one-dimensional line. So now let's just plop a whole bunch of particles on this one-dimensional line and see what happens with their interactions. I just used a neutral boundary so that I could distinguish which particles are being entangled at which time. So the standard particles can interact and entangle as well as the Susy particles. After this entanglement, two things can happen: either persistent entanglement or the exchange of entanglement. The exchange of entanglement is basically equivalent to quantum fluctuations, and persistent entanglement is equivalent to things with mass and with gravitational pull. Now the specific distance of these non-local entanglements on this neutral boundary could possibly tell you the size of the mass within it. So if the Susy entanglements are super far away, then you have a big ass mass. Or if the entanglements are super close, then you have a small mass. Here's just another example of me going a little buck wild and adding a whole bunch of random particles on this neutral boundary. On the left you can see that there's no mass, it's just an exchange. On the far right you can see that there's some standard mass and some Susy mass, and in the middle within the Susy bounds you can get exchanges to occur, you can get standard masses, and so on and so forth. So basically I feel like there could be a crap ton of different combinations or interpretations, but if you zoom in on a specific section, then you could distinguish what is actually happening. One of the key distinctions between ADS-CFT and de Sitter space is the nature of their boundaries. ADS-CFT has infinite boundaries, which is where the conformal field theory CFT resides. And the Sitter space would have finite boundaries at finite distances. One thing that's really confusing me is, well, if we have forces with infinite range, such as gravity and electromagnetism, how do finite boundaries explain those forces? So while the forces themselves might be considered infinite in principle, their observable effects within the finite universe can be limited by the cosmic expansion. Okay, this is me just reading off ChatGPT. Could this explain the breaking of supersymmetry? So basically, as the universe was expanding, all of the Susy entanglements were expanding with it. Hypothetically, could we say that dark matter or these Susy boundaries not only helps to provide the stability of galaxies, but atoms and shit, like fundamental particles, so that all entanglement boundaries provide stability to all bulks within, no matter the scale. Okay, I want to show you the wave probability density of the hydrogen atom. This basically just tells you where we think the electron will be based on the energy level of the atom and the orientation of the atom. Remember when I said that the non-local entanglements could fluctuate in distance? So what if that is happening based on the energy level of the atom? So everything that is not pink is the probability density of the electron. So from purple to orange to yellow to white. So that's all the electron. But everything that is pink is my speculative idea for where these Susy particles may be based on the energy level of the atom. If we look at the 200 and the 300 example that I have at the bottom, basically when the atom gains energy, the electrons move farther away from the atom, and so they go into their respective shells. When the atom gains energy, the Susy particles are pushed in. More Susy particles are pushed in depending on the energy level, and more electrons are pushed out. So the higher the energy, the more non-local these electrons are, and the more local these Susy entanglements and their particles become. So could we then infer that the lower the energy state of the proton, the more non-local these Susy entanglements are? I don't know how non-local, but relatively non-local. But the higher the energy state, the more local they are. In regions with zero probability density of the electron, those are called nodes. That is where I think with 100% probability the Susy particles are. This is going to be quite a stretch, just like everything else in this video. But basically the radial nodes are where the Susy particles are, and the angular nodes are where the Susy particles are and their entanglement planes. The literal boundary for these standard particles. For the example in the top left corner, the z-axis is where the electron has 0% probability of being found, and that is where I think the Susy particle probability is and its entanglement plane. So another example of what I think the atom could look like, note that the non-local particles and their entanglements are still probabilistic. Here I was just wondering, well, depending on how the matter is structured inside a black hole may determine the order of operations going outside the white hole. So, for example, is it FIFO or LIFO? Yeah. Here's some random shit. There's some more shit. Here is all of our antimatter. Well, hypothetically, let's just look back at our previous universe and the parent black hole that would eventually create our universe. The Hawking radiation for that parent black hole, the antimatter and matter entanglement pairs created at the event horizon, what if antimatter rarely enters a black hole? Or, for the case of our universe, more matter just so happened to enter the black hole than antimatter. Tachyon. These are particles that are born traveling faster than the speed of light. Now, hypothetically, let's just say that when the event horizon of a black hole forms, those Susy entanglements, those particles, become tachyons, because whatever falls in its boundary cannot escape because it's traveling faster than the speed of light. So all light will not be able to escape. But like if particles already have mass, it's literally impossible to travel at the speed of light. So I don't know, it's hard to think about. Since photons don't have mass, I don't think they're connected to any Susy entanglements. And if they did, they would have to haul around these particles, and I just don't think that makes sense. Now, because electrons do have mass, they do have these Susy entanglements, and they do have to haul them around. Maybe that is the discrepancy between the speed of light in a vacuum and the speed of an electron within the orbit of an atom. I was just trying to think about, well, which bulk could have the more non-local entanglements? So for example, would it be the electron or would it be the proton? Which boundary would be more non-local? Okay, here I was just trying to think about, well, what if we just treated the universe itself as a particle? And basically, what would happen if that were the case? Well, the universe could be in a superposition of states. It could maybe decay into smaller universes. Maybe it is absorbed or repelled by other universes in its universe. How do the actual boundaries themselves interact with each other? So how do Susy entanglements interact with standard entanglements? Maybe they all repel each other? I have no idea. Alrighty, last but not least, hypothetically, let's just say that the black hole does compartmentalize the matter within it. What if that is similar to the way that atoms compartmentalize the electrons around it? When atoms are in lower energy states, the electrons are closer to the nucleus, and the Susy particles are farther away. When atoms are in higher energy states, the electrons are farther away, and the Susy particles are closer to the nucleus. Now, the opposite would be true for a black hole. So a black hole with higher energy would have all of its standard matter falling in and all of the Susy entanglements farther away. And a black hole in lower energy would have the standard entanglements farther away and the Susy particles closer to the quote-unquote nucleus or singularity. The real question is, if a clown farts, does it smell funny? I appreciate you for wasting your time in watching my video. I must reinstate that I am not a physicist, and I am not trying to spread misinformation. I just want to share a cool idea. I don't know if it makes any sense to any real physicists. That's okay, because I'm not trying to prove anyone wrong. I don't want to step on anyone's toes. I just want to bring my idea out to the world, and hopefully it could spark some interest back into the physics community, because I know it's in a rough patch right now. Thanks. Peace.